So please start.
Thank you very much for the introduction, and thank you very much for the invitation. So, so really my pleasure to give a talk in chaos, right? So, yeah, so Zhanggu asked me to talk about my recent work about direct detection of freezing inelastic dark matter. So it will be, and so this is the work done with the postdoc at Tsinghua, Da-Neng Yang, and based on this work. Okay. Oh, okay. So yeah, I think for this audience, I don't have to talk too much about motivations to do research in dark matter physics, right? So because we know there are already a lot of evidences about the existence of dark matter, right? So we have evidences from almost all the scales in our universe, from small to large, from the observation of the galactic rotation curves, and also from this. Also from the large-scale structure, survey, and comparing it with numerical simulations. Okay, so this is actually a larger scale. So for smaller scale is this one, right? From the bullet clusters, and also from this gravitational wave. Also from this gravitational lensing effects. And also from this type 1a supernova, we can measure the total energy density of the universe. So together, and also from the CMB observations, and together all these observations give us these evidences of the existence of dark matter, and also all these observations give us hints that give us the same composition of our universe. That is the ordinary matter composed by standard model particles, only composed of about 4% of our universe, and the 23% is called dark matter, and the other 73% of the energy density is called dark energy. Right? So why dark matter is special, and why there are a lot of searches for dark matter? That is because dark matter is matter-like, right? What does it mean by matter-like? As the dark matter, we can have energy density and pressure. But for dark matter, the equation of state, just from all these measurements, it tells us that the equation of state of dark matter is matter-like, which means the pressure is much smaller than the energy density, right? And we know that to build the fundamental framework of our standing to our universe is based on quantum mechanics and relativity, right? And we know that in relativity, the theory, right? The theory of relativity must be covariant. That means must be Lorentz invariant, right? Must be Lorentz invariant. That means the things in our theory, right? The framework of the theory must be Lorentz invariant. But if you have something matter-like, you know it must be something. It is not some constant in our theory. It must be something, right? So like the difference is it's a dark energy, right? We know that dark energy by itself, it is something like a vacuum energy, and it is totally covariant. So it is okay. We can just put a constant in Einstein's equation to get dark energy. But for dark matter, it is completely different. It must be something, right? And for particle theories, we want to assume that the dark matter is something like a particle, right? And so we want to search for the particle nature of the dark matter. So what are the particle natures we want to search of? So we want to know the mass, the spin, the size, and maybe any internal structures, and also if it has any interactions with standard model particles other than gravity. Also, we want to know if there's a self interaction in the dark matter sector other than gravity, right? So these are the things we want to know from the particle physics side. So right, so. But what do we have know already, right? What do we know about dark matter already? So basically, we only know the existence of dark matter from gravitational effect. That's it, right? And for the information for particle physicists, right? What do we know? We know that the dark matter right now is composed by non-relativistic particles, and the most important thing I think is that we know it's relic energy density. It is about 5 times of the energy density of baryons. That is very important. And also to do the direct detection, we know the local density from simulations. That is about 0.3 GeV per cubic centimeter. And we also know that the dark matter doesn't have strong long-range interactions, right? And we also know that the dark matter cannot radiate a lot, because we know that dark matter forms halos, right? So that means the dark matter, most of the dark matter cannot collapse onto the disk. And also we know that the interaction must be weak since we have this bullet cluster constraints, okay? And so these are the evidences. These are the things we know. And I think the most important is the measurement of the relic abundance, right? So any successful dark matter models must be able to explain, right, why today we observe the energy density, today's energy density of dark matter, okay? And so we have a lot of models which can understand the relic abundance of dark matter. So we have the freeze-out models prevailing for about 70 years, right? So the most important one, I think, is the WIMP model. And we also have freeze-in models. And we also have QCD axions, and then the production mechanism is something like a misalignment. And we also have, in recent years, dark photon dark matter models. And so in these models, dark matter usually produced during inflation. And so today I'm going to focus on this freeze-in model, okay? So here's the outline. And so I will first give a basic, very brief basic introductions about the freeze-in mechanism. And then I will talk about the direct detection. So, and then I'm going to talk about detailed models, right? Detailed models so that we can do direct detection. So in order to do the direct detection today, to see some signal today, right? So I will show you that the ordinary freeze-in model cannot, so basically it's very secluded from us. So basically we cannot see it. And to be able to see it today, well, we must introduce the inelasticity in the dark sector. And and then we need to, so because we introduce inelasticity, we have a ground state of dark matter, and we also have an excited state of dark matter. So then during when the dark matter coming in, right, if the dark matter coming into the detector is the excited state, and then it can collide with maybe electrons in the target, and then it will go into the ground state, and then this the gap energy will be released to the electron, and then the electron will be kicked out, and we can see the signal, okay? And so that means we must, to do the direct detection, we must assume that there's a sizable fraction of the excited state exists in current universe, today's universe, right? Or we cannot do the detection. And so to do that, we must first calculate the fraction, because we know that there are a lot of processes for the excited state to become the ground state, right? From decay, either from decay or from the scattering, okay? And so in our model, so in the scenario we are going to give in this talk, so the dark matter are relatively light, so about MeV scale. So then MeV scale dark matter can actually be produced inside inside supernova, okay? And so there's a constraint from supernova. That is what we are going to talk about in this part. And also we know that this so just during the preparation of this work, so this XENON 1-ton anomaly suddenly popped out, right? Because there's a XENON 1-ton anomaly, and because we are also working in direct detection of dark matter, right? So we should be able to explain it for the paper to be published, right? Or people will ask, can your model explain this anomaly, right? If we can't, right? So then why you want to write a paper at this moment, right? So, in the last part, I will talk about using this model, using this scenario to fit the XENON 1-ton electron recoil access, okay? And then I present the result, and then I will summarize. Okay, so please stop me if you have any questions. So here's the very basic introduction of the freeze-in model. So in the freeze-in model, so the basic assumption is that the inflation sector, right, only during reheating, right, so only coupled to the standard model sector, so that when at the end of inflation, the inflaton field will only reheat the standard model sector. And then it is usually assumed that there's a very weak portal between the standard model sector and the dark sector, okay? So that after the standard model sector is reheated, its energy density will be very slowly leaked into this dark sector through this dark portal, right? And so this idea actually has been around for about 40 years, right? All the way starts from the people's understanding of neutrino physics. So when people want to introduce stereo neutrino, usually the process is a freeze-in process, right? So it actually starts from this paper, And also in 1987, Anish Monohar has started a case to freeze in a particle in a very general case from a thermal bath. And then in 1993, it's a very famous paper by Dawson and Wistrow to use this freezing mechanism to introduce a warm stereoneutrino dark matter. Okay, and then this mechanism is re-emphasized by in more general cases by Lawrence Hall and collaborators in about 10 years ago. Okay, so as a basic introduction, okay, so we need to, so as a dark matter model, right, as a successful candidate, it needs to explain today's relic abundance, right? So to calculate today's relic abundance, what shall we do, right? So we solve the Boltzmann equations. So here's this is the Boltzmann equation for the evolution of the energy density of the dark matter. So this ND is the number density of dark matter particle, and this H is the Hubble expansion rate, and this NSM is the number density of a certain kind of standard model particle, and this gamma is the conversion rate. Basically, this gamma is the conversion rate for a certain standard model particle to be converted into dark matter particle. Okay, and we will discuss the explicit form of gamma later. Okay, and so usually when we solve the Boltzmann equation, we introduce we change the variable from this time t to the temperature t, or capital T, okay, through this relation, okay, and then we can combine these first two terms, and then so that we can simplify the Boltzmann equation into this form, and also and if this standard model particle is relativistic, we know that the NSM is just proportional to t to the cubic. And the coefficient of the proportionality is actually order 1 number, right? So that we can neglect it. So then the Boltzmann equation just simplified into this form. And now it's very easy to solve, right? So before solve the Boltzmann equation, so we need to use the fact, almost the only fact we know about dark matter, which is the relic abundance. That is the number 5, right? So the 5 is the ratio between the dark matter energy density to the baryon energy density. And it can be rewritten in this form, and this NB is the baryon number density, and MB is the baryon mass, right? So today the baryon mass is about 1 GeV, okay? So the mostly proton and neutron. So then, so we can relate this NB, the number density of baryons, to the number density of gamma, right? And so we can write it in this way. This eta gamma is actually a known number. It's about 10 to the minus 10. So, and then we reorganize these two factors into this form, and this ND divided by the temperature. So this is what we can calculate from the Boltzmann equation, right? And here, this factor, this MD divided by MB times this is also the number we don't know, right? And it's related to the mass of dark matter. So these two numbers I actually know, right? This is 10 to the minus 10, and this is about 1 GeV. So now we can just calculate. So from the Boltzmann equation can give us information about this number, this ND divided by T to the cubic, okay? And so just from this equation, it's easy to solve, right? We just integrate.
Excuse me.
Yes?
What is eta gamma in your formula?
Yeah, because this NB is related to N gamma, right? Through this eta gamma. And N gamma we know is a known number, so it's related to the CMB temperature.
Oh, okay.
Yes.
Thank you.
Okay. Thank you. So then we just can solve this Boltzmann equation by just directly integrate this gamma t, right, all the way from the initial time to today, right? What is the initial time? It's actually related to the reheating temperature, and the reheating temperature is so we can just do a change of variable from this time t into the temperature, and then it can be written in this way. Okay, so now we are going to so the freezing models can be separated into two scenarios. One is called the IR freezing, and the other is called the UV freezing. So what does IR freezing mean? So we just take a look at this this integral. If this integral is dominated by in the in the high temperature region, in the UV region, then it is called the the UV freezing, right? So it's like it's this. And if it is dominated by the IR region, right, then it is called the IR freezing. So the advantage of the IR freezing is that it is insensitive to the reheating temperature and to the high energy physics, right? So only low energy physics determines the energy density, the number density of so this quantity, right? So this is the number density of dark matter per unit entropy, right? You can see it as entropy density. And so, but for UV freezing, it's actually very sensitive to the reheating temperature. And so in this talk, we will focus on this IR freezing scenario. Okay, so it's actually natural for freezing dark matter model to be IR freezing. Why is that? It's because if we just introduce marginal interactions, then it is so if the theory is like renormalizable, right? Then this freezing is just automatically to be IR freezing. So why is that? It's just like this. So then the interaction we know. So the interaction is gamma t, right? And consider a theory. Consider a theory. So we know that the dimension of gamma is 1, right? And also we know here there's h, and we know that what is h? H is just t squared divided by m Planck, okay? And so in a theory, if the theory is a marginal theory, that means there's no scales, there's no important energy scales in the theory. And then in the thermal bath, the only important scale is the temperature, right? So then gamma t can be written as in the form of alpha to some power, the coupling to some power, right, times a temperature, just from dimensional analysis. And then so then that's we can just put this one, this gamma, and this h into this integral, okay? And then once we do it, we can just see that this integral is actually IR divergence, right? So what does IR divergence mean? IR divergence just means that the IR part contributes the most, okay? So we can just neglect this UV effect, any UV effect, which doesn't matter. So any like higher dimensional, heavy degrees freedom will be automatically coupled from this calculation, okay? And so we know that this IR divergence must be cut off, okay? So then what are the possible cutoffs as are these, right? So first of all, it's the dark matter mass. So if the temperature temperature becomes smaller than the mass of dark matter, then we know that dark matter cannot be generated, okay? So this is one of the cutoff. And then if the mass of dark matter is smaller than the mass of the electron, we know that if the electrons are all annihilated, right, in the standard model, okay? So we know that it cannot be all annihilated because the lepton number variation. But if the large part of the electrons annihilated away, then there's no plasma, right? If there's no plasma, there's no such interaction, okay? So there's no way just to generate this dark matter. And also there's a mediator mass, right? So the mediator, so if the mediator, so for IR freezing, what we assume is that there's no large scales in the calculation, right? But if the temperature is smaller than the mediator mass, then the interaction just becomes higher dimensional interaction. And then the freezing scenario just changed from IR freezing into the UV freezing, right? So basically this MV is this mediator mass is just another possible cutoff, okay? And so the prevailing scenario is that, so I think most interesting scenario is the following. So if the dark matter mass is much larger than MV and ME, what will happen, right? Then the MD is just this cutoff. Then let's just do this calculation. Then the ND divided by T to the cubic just give us this, right? Because we want to cut off this IR divergence of this T integral by MD. Then the results just like this, okay? And then what we are interested in is actually the energy density instead of the number density, right? And so the energy density can be written this way as ND times MD. And what we can see is that this MD, the factor MD here and here just cancel, okay? So then basically this number 5 that is not sensitive to the dark matter mass if the dark matter mass is much larger than the mediator mass and the electron mass. So in the end, if this is the scenario, then what happened is that we can just get a very conclusive like a conclusion, right? So prediction that this alpha to the nth which is the combination of all the couplings, should be roughly determined by this number, this n gamma times mb divided by m Planck, which is about 10 to the minus 28, right? So basically, given a Friesian model, and you tune all the parameters to this number, and then you get this, you automatically get this observed energy density of dark matter. So any questions? Okay, so now this gives us it is very challenging because the number is so small, right? Just by eye, you can see this number is so small. So how can we do direct detection to this? Okay, so usually people saw that. So this is actually people know it is very difficult to do direct detection or to search any signal, right, from Friesian dark matter models. And so in today's talk, what we are going to do is that what we are going to show is that in today's direct detection experiment, we already have the ability to search for Friesian scenario in some, at least in a very small part of the parameter space. And with the future experiment, right, with the future like even larger experiment like XENON n-ton, or maybe XENON, or maybe the future Darwin experiment, we can just even further explore more parameter spaces in this Friesian scenario. So that is the main theme of this work. Okay, so to study the direct detection signals or to set any constraints, right, we need to introduce a detailed model, right? So the model we are going to study is the following. So basically, it's a model about the portal, right? So what we assume is that the portal is a dark photon portal. So basically, we introduced a vector boson, a new vector boson, and with a tiny bit of mass. And because it's a vector, we can just write down a T mu nu. And we know that the T mu nu, we can just write down a kinetic mixing between our photon and this mediator. And the mediator, we call it dark photon. So then the mixing, the interactions can be written this way. And so we assume the only interaction between the dark sector and the standard model sector is through this dark portal. And in the dark sector, we introduce a dark current. And so we just write down the interaction between this new introduced dark photon and this dark current, okay? And so to have a signal, so basically this work is like a data driven, right? So we want to have a signal. So we just want to consider the cases that we can get a large, as large signal as we can, okay? So it turns out that to have the signal, we must have this, the spectrum must be look like this. So this MV must be between the MV is the mass of dark photon, must be between 2 times of the electron mass and must be smaller than 2 times of the dark photon mass. So why is that? If the dark photon is larger than 2 times of the dark matter mass, then once the dark photon is produced, it's frozen in, it will mainly decay into the dark matter, right? So that means what will determine the dark matter relic abundance? It will be the kappa. It will be the kinetic mixing, right? The dark coupling will be irrelevant to the production of the dark matter, okay? Because once the dark photon is frozen in, it will all decay into the dark matter, okay? But the direct detection, we know that it is related to the product of kappa and E dark, okay? It is related to the product. But we also know, as we will see later, the E dark must be small, okay? E dark itself must be small. So that means if this mediator can decay into the dark matter directly, then the signal will be further surprised, okay? So that is why to have a signal, we want to set this MV to be between 2 times ME and 2 times dark matter. So why it must be larger than the 2 times electron mass? So that it will decay into the electron, or it will overclose the universe, okay? And so in this specific regime, so if we want to get a correct relic abundance, it turns out that this product kappa times E dark must be between 10 to the minus 11 to 10 to the minus 12, okay? And so this is the number we want to, we are going to use to do this direct detection, okay? So, okay, so we can just, in this regime, we can just estimate, okay? We can just estimate the number density of the of the number, no, not the energy density. So in this regime, we want to, so because we want to do direct detection search, right? We want to first estimate the number of events, right? If it's too small, then we don't have to write a paper, right? So basically, if we assume it is elastic scattering, we assume if the dark matter can collide with the electrons elastically, right? Then there's a cross. We can just simply estimate this cross section, and this is mv to the fourth, because the energy transfer is usually much smaller than the mass of the dark matter, or the mass of the mediator, right? So then it becomes a contact interaction, and we have all these factors. So this the coupling in the standard model set, and this is coupling in the dark set, and this is mixing. And this mu is the reduced mass between this dark matter and electron system. And then if we put all the numbers together, this is today's energy number density of the dark matter, and this is cross section. This is average velocity of the dark matter around us, and this is the total number of electrons in the xenon detector, right? In the xenon 1-ton detector, and this is the total lifetime of the experiment. Okay, so if we put all the numbers together and assume the lifetime is 1 year, and assume it's ton scale detector, and if we assume the dark matter mass to be about 1 MeV, then what we can show is just from this formula, we can have 10 events, okay, in the detection. So 10 events is actually, if it is background free, it is actually good enough to have some kind of like a discovery, right? So that is the motivation for us to do this work. However, there's still challenges, right? So here, what we assume is the dark matter mass to be 1 MeV. We know that the dark matter mass cannot be smaller than this number, okay? So if it's smaller than this number, what will happen? So basically, we cannot, we know that we cannot increase the dark matter mass. Why we cannot increase dark matter mass? Because if we because the number density is actually proportional to dark matter mass inversely, right? So if the larger the mass of dark matter, the smaller the event number. Okay. So but now let's compare this result with the current experiments. For example, for xenon 1-ton experiment. So this is their work last year about the electron recoil, right? So you can see that the best so we know that all the experiments has a threshold, right? What is the threshold for xenon 1-ton experiment? So they for electron recoil events, they have a cut for the electron kinetic energy to be about 1 keV, and to translate it to the mass of the dark matter, they can only sensitive to the dark matter mass to be about 20 MeV. Okay, so basically for mass of dark matter smaller than 20 MeV, for elastic scattering, right? They cannot observe anything. So now there's another experiment which is designed for this kind of low mass dark matter, which is called SANSA experiment, and they use something called the skipper CCD technology, and can lower the can lower their just a threshold for the recoil energy. Okay, and so you can see that they can actually observe. They can have a sensitivity for like 1 MeV dark matter, but still you can see that for our case, they didn't draw this freeze-in scenario here, right? It is very far. It is very far from so we can just say this. So the scale of this experiment is actually too small. So the current scale of this experiment is only a few gram. Okay, it is very small than ton scale. So here we claim we can have a signal for ton scale detectors operating for like 1 year. Okay, but for such a small detector, maybe in their like a final form of the SANSA experiment, they may have a sensitivity for the freeze-in model, right? So basically, the current experiments, if we assume the interaction is elastic, if there's no additional boost to the signal, right? So then the current detectors are not sensitive to freeze-in dark matter models. Okay, so a boost, basically, to have a signal, a boost is in need. Okay, so we have done some work before to use the sun as a boost, right? And to try to see if it can be observed inside the xenon detector or not. Okay, so and for sub MeV dark matter. But the thing is, if we use the sun to boost the dark matter, right? There's a penalty factor which is about 10 to the minus 5 due to the large distance between the Earth and the Sun. Okay, so it doesn't work because the rate is too small. So, and then we got this idea. So we cannot boost the signal using any of this kind of external sources, right? So what about the internal source? What about the dark matter has an excited state and a ground state? And what if this the dark matter particle flying in this detector is the excited state? Okay, and if that is true, then if the excited state can just during the collision, if the excited state can be converted into ground state, and then the gap energy will be released, and then the dark matter will be, and then the electron kicked out will be further accelerated, right? And so then we may have a signal. So to have a detailed model, we can just write the model like this. So basically, we can just introduce. So we consider two models. One is the scalar dark matter model. The other is the spinor dark matter model, right? So for the scalar dark matter model, we can just first introduce a complex scalar, and that is coupled to the dark photon field. Okay, and then we know that because our dark photon is already massive, and so it doesn't matter if there's a mass gap, if we break this U1 symmetry of this in the dark sector, in the dark matter sector, right? So basically, we can give a small mass gap. We can split this real part and the imaginary part of this complex scalar a little bit, right? So if we do so, you can so after a few just a very simple calculation, you can show that the coupling between this the coupling between the dark photon and the dark matter is actually off diagonal, right? So basically, the dark photon couple, the vector field coupled to chi1 and chi2, okay? And so then if in this scattering conducted by this dark photon between this dark matter and the electrons, it will automatically convert the chi2 into chi1. And the same story happened in the spinor sector. We can first introduce a Dirac spinor and let it couple to the dark photon. And then we introduce a very tiny Majorana mass. And then without any parity variation, if we don't introduce any parity variation, then the coupling between this dark photon field into the dark matter field is actually off diagonal, okay? And so with this interaction, it can just conduct the inelastic scattering process between the dark matter particle and the electrons, okay? And so in the scalar model, there's actually another additional term, right? So additional marginal interaction. Basically, it's the 4-point self-interaction of this scalar field. And after we introduce a mass splitting, it will also generate a scattering between chi1 and chi2. And we will show that this interaction is actually very crucial for us to have a signal. And to introduce this sector, this interaction is actually not relevant to the scattering of dark matter with the electrons, right? But why it is important? Because it will change the relic abundance of this excited state, right? So in today's universe, as we will see later. Okay, so yeah, just as what I said. So to calculate the direct detection signal, we need to know the fraction of the excited state during the in today's universe, right? Because because it is not a ground state, so there are actually several ways for it to be converted into the ground state during the evolution of the universe. So the first one is the decay, right? So because there's a mass gap, it can actually decay. However, we know that the mass gap we need is actually very small. It is actually can be much smaller than 2 times of the electron mass. So that means it cannot decay into an electron-positron pair. So then the only decay channels are the first, just like the decay of the dark photon field, right? So it can decay through an electron loop into 3 photons. And the other decay channel is through the mixing with the Z boson into 2 neutrinos, okay? But both of them are actually super tiny, okay? So that's why the dark photon can be, that's why in some models, very light dark photon can be dark matter, right? So it is very easy to show that this the excited state is actually cosmologically stable, okay? But it cosmologically stable is actually not enough for us to calculate, for us to have enough chi2, right, to do the direct detection. So there's also a process that the 2 chi2s can actually collide with each other in the early universe and to produce two chi-1s. Okay, and we know that when the temperature is, if the temperature is smaller than the mass gap, then then actually there's the inverse process cannot happen, right? And so from this fact, this dark coupling must be small enough so that this process, so that we have enough excited state today for the direct detection to happen. Okay, so now, because this is very crucial for direct detection, we need to calculate it in detail. Okay, so now let's try to do the calculation. So we are going to calculate this process, right? So this process is just like the freeze out process of dark matter. Okay, so basically we are calculating the freeze out of Chi2 in the early universe, and we know that the freeze out process. So there's no inverse process. Excuse. Okay.
Yes, just one more question. But the abundance of Chi2 is still small in this mechanism, right?
Yes, it can be like order 1 if the coupling is small. Yeah, and it can be small if the coupling is large. So I'm going to calculate in the following slides. I'm going to calculate this fraction of Chi2.
Okay. Yeah. What I wonder is how can this annihilation channel be relevant in the freezing mechanism assumption that you have? Because
yeah, in the freezing assumption, it's actually Chi1 and Chi2 are frozen in together, right? Because this is this one. Yeah, because you can see this interaction is actually off diagonal. So once you frozen in, once the Chi1 and Chi2 are frozen in, you can see that you have one Chi2 and you have one Chi1, right? They always come in pair.
Yeah, yeah. And then after that, this annihilation takes part.
Yes, and then the annihilation will make F2 smaller, right? And so the initial condition for F2 is like 0.5.
Mm-hmm.
Yes.
Okay.
And so in the following, we are going to calculate this, this process. Basically, to determine what is F2, we need to solve the Boltzmann equation for this annihilation process, right?
Mm-hmm.
Yes. Okay. So now let's start to do this calculation,
yes,
right? So, yes. Okay. So the frozen in, the freezing process actually happens because it is air dominant, right? So it happens when the temperature of the standard model sector is roughly equal to the mediator mass, which is roughly in this work is also roughly equal to the mass of the dark matter. Okay, so that means when the dark matter particles, when Chi1, Chi2 are frozen in, they are actually non-relativistic, and because they are non-relativistic, the temperature in the dark sector actually scales as a to the minus inverse to a to the minus 2, right? As a to the minus 2 because it is actually matter-like. Okay, we know that the velocity always scales with a to the minus 1, right? So for the kinetic energy, scales with a to the minus 2. And because they are non-relativistic particles, most of the temperature is actually determined by the kinetic energy. Okay, and so basically the temperature in the dark sector is actually determined in this formula. So the relation between T dark and T standard models like this. Okay, so there's a square dependence. And this eta T is the coefficient of proportionality. It's actually order 1. We can actually do a detailed simulation to determine that eta T is order 1. It's just almost equal to 1. Okay, so now let's try to solve the Boltzmann equation. This is just a little bit new, right? So it's a little bit different from the dark matter dark matter freeze out because it is a conversion between two non-relativistic particles. Okay, so this is the Boltzmann equation, and usually, so we define this fraction F2 as this. Okay, and F1 is automatically 1 minus F2. And just as usual, we define two parameters, x as the gap divided by T standard model. We also have two temperature scales in this calculation, right? And x dark is delta divided by TD, okay, by the dark matter temperature. And then after all this redefinition, we can just we can rewrite this Boltzmann equation in the following form: is df2 divided by dx, okay, and roughly equal to this. okay, roughly equal to this. And so this B is defined in this H, right? So it is a combination of the number of degrees freedom and also some pi's, right? Some factor of pi's. Yes, it's a constant, okay, order 1 constant. So to solve this equation, we need first to calculate this cross section, okay? So the cross section is actually determined by 2 diagrams in the simplest model, right? And because this process becomes important when the temperature in the dark sector to be smaller than the mass gap, okay, than the mass gap, which is actually much smaller, because we want the mass gap to be about 1 keV, right? So for the xenon detector to be sensitive, okay. So then this mass, and then the dark matter mass is around MeV. So basically in this calculation, this T dark is much smaller than M high, okay. And also it is also, so we can do this calculation in our relativity limit. And also this T dark is much smaller than MV, so that we can just first integrate out this dark photon and to do it as contact interactions. Yes, so in these limits, actually the 2 diagrams are equal to each other. So basically the calculation becomes simplified. And after some simplification, so we can, the cross section, the sigma times average of sigma times V can be written this way. This F's are the initial, distribution of the initial states. So we need to calculate 2 processes. One is Chi2, Chi2 to Chi1, and also the inverse process, right? And so these are the phase space factors when we just integrate out the final state, right? So we always have this final state form factors, and this S is the square of the center of mass energy. And so because we treat it as a contact interaction, we always have this E dark to the first divided by M mediator mass to the fourth. Okay, these are simple, and the 1/2 is because it's the final states are just identical particles. Okay, so so very fortunate that this we can just solve this Boltzmann solve this cross section analytically. Okay, so once we do it, so this cross section can just be written this way, and this F 11222 and 22211 can just have the same forms and can be written in Bessel, can be solved in using Bessel functions. This K1 is some Bessel function, right? So yes, and this, so for the 22211, you can see this, you have this factor, this E to the X dark, and for 11 to 22 process, you have E to the inverse X dark, right? So this is completely makes sense, because if you put them together, you can just rewrite the Boltzmann equation in this way, okay? And so here there's a factor E dark here, and this is E to the minus X dark. So from these are actually dictated by the detailed balance principle, okay? So these are just the difference of this Boltzmann distributions, as you can see, okay. And so this capital A just includes all the factors, right? All the factors in this process. Basically, the first factor here collects all the information of the evolution of the universe, okay, such as here. And the second factor includes all the particle physics informations. You can see it's this is the interaction part, and this is the mass part, the phase space. Also, the phase space part is in this delta. Okay, so how large it is? So this A is about 0.37. So it is can be order 1 if we choose these numbers. Okay, if we put in this like typical numbers. So basically, in this process, A just in the parameter space we are interested in, as A is just can be automatically around order 1, right? Maybe 0.1, 0.01, right? So basically it is not very small, what I just want to show. And so now we can just, with this factor of A, capital A, we can just solve this Boltzmann equation numerically, okay? And so this A is the only like unknown number. So this F2, this is the F2 today, if we solve this Boltzmann equation. And you can see if A is super tiny, right? If A goes to 0, then it just saturated by 0.5. This is the initial value of F2, okay? And if A becomes large, this F2, there's a very simple relation. F2 just goes like 1/2 times A. So we solve this just Boltzmann equation numerically. And also, so we also need to consider, because in our in the region we're interested in, right? So everything is like in MEV scale, and as I said earlier, so then that means that the dark photon and also the dark matter can be produced inside the supernova, right? And then there will be a constraint, and so these people did a very nice work to basically calculated the supernova constraint for the dark photon emission, okay? And their constraint is like this. So the kappa, kinetic mixing, this should be kappa, okay? And this should be MV. And so the kappa for the kinetic mixing must be smaller than this number, okay? This is because, so what they consider is the longitudinal production of the dark photon. And so basically for lighter dark photon, it is more and more difficult to produce it in the plasma. That's why this constraint becomes weaker for smaller, for lighter dark photon, okay? But this is the constraint. And so this constraint, we can just directly convert this constraint into F2, okay? Into F2. So basically, this means the F2 must be smaller than this number, something like 10 to the minus, 2 times 10 to the minus 3, okay? Smaller than this number for typical values we're interested in. Okay, so now let's talk about the xenon one-ton access, okay? So what is the xenon one-ton access? So what is the xenon one-ton detector, right? This, I think for this audience, I don't need to talk too much about it. It's basically, it can detect 2 signals. One is S1 and the other is S2, right? And they can use these 2 signals, they can use these 2 signals to just distinguish if the signal is from electron recoil or nuclear recoil. And also what they found is that they found access. So what is this access? As they found access between 1 and 7 keV in electron recoil events. So the background they expected is something like 232 plus minus 15. Okay, the error is 15. And what they observed is 285. And so a very simple calculation can show us it is like a 3.5 sigma, okay, away from this expected background. Okay, so there's access, and for us, because we are starting this scenario, right? So and it is just in the range to fit the signal, right? So it must be able to fit it, so that we can publish a paper, right? So now we just do a calculation. So what is the? So basically, this is the formula for the recoil spectrum. So basically, what they publish is a spectrum, right? We need to be able to fit this spectrum. So basically, the spectrum, this is the recoil spectrum, and it is determined by these factors, basically a velocity distribution, and also these form factors, right? So describe how this dark matter interact with the atoms to kick out the electron. Okay, and so this part, this psi is the bound state wave function of the electron, and so this part is actually the e to the minus ikx is the plane wave approximation of the outgoing wave function, right? But we know that there are subtleties there. The first one is that we know from the basic principle of quantum mechanics, the ground state wave function and the scattering and the outgoing scattering wave function, right? They belong to different eigenvalues of the Hamiltonian, right? That means they must be orthogonal to each other. So that means we must subtract this we must subtract the bound state part from this plane wave, or we will get a large signal, unexpected large signal. Okay, so then this result will be inaccurate. And then there's another effect that because the electron is charged, right? We know, and also the ions with the electron kicked out is also positively charged, right? And so there will be a long-range interaction between them conducted by photon, right? And so this reminds us there must be something like a Sommerfeld enhancement factor in this result, okay? And so there are people calculated this result for different shells of for electrons from different shells. And basically for different orbits or different shells, this the Sommerfeld factor can be written this way, and with this effective charge of this ion with the electron kicked out, right? And so basically, because the electron it might be the electron from the inner cells, right? So then the Z factor can actually be large. Okay, so you can see this is the effective number of this Z factor. And so basically, in the realistic calculation, we should replace this plane wave the plane wave to this one to get this the more accurate form factor we need to use. Okay, and so this is the spectrum. You can see this is spectrum, and so the colored curves are the recoil spectrum from different orbits, right, of the electrons. And so this is the black curve is the combined. You can see that it is a peak-like, right? The peak is because it is most of the energy is actually from this gap energy of the excited state. And so basically with these parameters, with the choice of these parameters, we claim that we can.
Excuse me. In the previous slide.
Yes.
So what is the dashed gray dashed line curves? You have a gray dashed curve.
Yes. Yes.
Without legend. So what this curve corresponds to?
Actually, I don't remember. Yeah, I know. I remember. Yeah, this is the this is the curve if we
ignore your effect.
Ignore.
No.
No. This is not the curve.
Without your implementation of this wave function modification and the Sommerfeld enhancement.
Yes, without those, and also without the effect of bound state. So I think this is the one. Yes, if we assume they are free electrons. Yes, if I remember correctly. Yes.
Okay. Thanks.
Yes, and so basically with all these with this choice of parameters, so you can see this is yes with this number. No, this F2 number is actually not correct. So sorry about it. So the number of F2 is something like 2 times 10 to the minus 3. Okay. 2 times 10 to the minus 3. Okay, so neglect this F2 number. Yes. So then with these numbers and with F2 2 times 10 to the minus 3, we claim that we can just fit this anomaly. And also if we tune this delta to be a much larger value, we can just have a peak somewhere else so that we can actually give a constraint. Okay. And so basically we calculate so here with this with the choice of these numbers, so with different choices of the gap energy and also the choices of this F2 number, we can actually have something like some constraint curves. Okay, some constraint curves in the parameter space of MD and MV. Okay, so yes, and so this shows the best fit region of this. So this shows the best fit region for this with different values of M dark and MV. So and also F2, right? So basically this is a so this is a best fit from this is a F2 x-axis is F2 and the y-axis is M dark, and this is the best fit region for MV. So basically with these choices we can fit the signal. Okay. And now, if we impose the constraint from this from the supernova, we can see that it is actually very marginal for us to fit this to use this model to fit the Xenon axis, right? So basically, this supernova axis just told us that the F2 must be something for typical values must be smaller than 10 to the minus 3, right? And so this is just this marginal value, right? You can see this marginal value of F2 of the best fit value, okay? But this is actually in the case of the simplest model without, so how to solve it, right? So remember, we have another term, which is the self-interaction, which is a self-interaction term of this dark matter particles in the scalar, in the scalar model case, right? So we always have this interaction. And also for the stabilization of the vacuum, right? For the vacuum stabilization, this lambda must be positive, okay? This lambda must be positive, and the effect of this lambda so always cancel with the tree level with the T channel diagram, if you remember the T channel diagram in this 22211 process, okay? So basically, once we have a lambda, just this process for the downscattering of the chi2 to chi1 in the early universe can just become smaller, okay? And so basically to fit this XENON 1 analysis, right? So basically, if we have something like a 60% of cancellation, we can just comfortably fit this analysis without just like a marginal value, okay? And so this is the result with if we invoke this lambda. So basically, we redefine lambda effective in this way, right? Basically, if we choose lambda, so we choose this lambda effective to be 0.6, which means it's about something like about 30%, 60% cancellation, right? Then you can see that between this dashed curve and this black curve, the black curve, right? This region we can fit this like XENON anomaly, and also if we allow us to have something like 90% cancellation, okay, and then the parameter space to fit this XENON anomaly is even larger, okay. So you can see that basically between this black curve and this black one can be for in the case that MV to be 1 MeV, we can just fit this anomaly, and basically if so basically the region between the dashed curve and with the solid curve with the same color, right? If that region overlap exists, then basically in that choice of MV, we can just fit this anomaly. Yeah, and so, but for fermion models, it's not, there's no such self-interaction automatically, right? So basically means so we must introduce new particles or maybe introduce new like effective operators in order to solve this problem, to get a smaller to get a larger F2. Okay, and so here's the summary and outlook. So basically what I show is that the direct detection experiments start to be sensitive to inelastic scenarios of freezing models. And also basically even more, we can just find parameter space to fit the XENON 1 anomaly, okay? And also there's an interesting fact. So basically to enlarge the parameter space in the scalar region, right? So we need a cancellation from the self 4-point interaction diagram to the T-channel diagram conducted by the dark photon field, right? And what we need is actually the lambda, what we need is actually very similar to the number of E dark squared, right? So is this a hint of supersymmetry, right? So we know that in SUSY models, this just can be automatically realized, right? So I don't know, right? So if this signal becomes true, right, maybe we are considering to enlarge this one to be supersymmetric models to have like more like better motivations. Okay. So that's it. Thank you.
Thank you very much. So any question?
I have a question. Have you mentioned on how you generate the mass splitting in the scalar case?
Just by hand, yes. We just softly break this U1 symmetry into a Z2.
Because I would say that in a complete model, let's say, you would need in order to generate this mass splitting, you would probably produce an additional channel between chi1.
Yeah, but that is true. That is true. But we can make that sector like heavier, right? As long as it's heavier than like a MEV scale, then it just doesn't matter.
Yeah, well, no, what I mean is that if you generate one additional channel through this, because probably, I mean, this chi would be coupled with a new scalar, and the scalar would just produce this splitting and so on. So which means that there would be another lambda in your theory.
Yes, maybe.
Would just change your conclusion about the value of this actual lambda that you have there.
Yes, yes, maybe. That is possible. Yes.
Okay, thank you.
So I think the if you generate delta M square by some kind of dark Higgs mechanism following the Krauss-Wilczek mechanism, then I think
Yes.
there could be additional contribution from the dark Higgs exchange, which also contribute to chi1 scale, chi2 scale interaction for the scalar case, and also psi chi1 and the chi2 case for the fermion case. I think, yeah.
Yes.
Okay.
Yes. Yeah, that is, yes, that is possible. Yes. And maybe
So,
in that case we can, yes.
yeah, I have one. So could you could you explain again how this stellar constraint arise?
Stellar constraint is just because the dark photon is only 1 MeV. And then so it just can be produced in the supernova.
Okay, just so it's independent of this scalar dark matter self-coupling, right?
Yes, it's independent. Yes.
Yeah, it's independent.
Yes,
Okay.
independent.
Okay. So did you start this work before General Anton the announcement, right?
Yes, we started. Yes, before. Yes.
I see.
Yeah.
It's interesting. Yeah.
Yes, and we just rushed to like finish it.
I see. Jonguk, can you?
Okay. Any other question or comment? I think there is no more question. So then let's thank Scott again.